to the organizers for this lovely opportunity, and thank you to the audience. Feel free to ask me questions. I'm talking about a project joint with Shuli Kang from Beijing Institute of Technology, and this one is on the archive. In fact, the more recent version is on the archive. So let me give the broader symplectic context. Look. Harder motivating questions in symplectic geometry. You have two symplectic manifolds. Are they symplectomorphic? And even for open subsets of R2N, this is a lot is not known, and this is an extremely interesting and non-trivial question. Of course, it is necessary that the open subsets be homeomorphic, and it is necessary that they have the same volume, but we know that this is not enough. And that we illustrate this with the very first example. Just straighten things out for the younger student in the audience. Well, the squeezing and non-squeezing. So let me do this specifically in R4, although we have analogs in higher dimensions. I could, on the one hand, take the Lagrangian product of two disks, two-dimensional disks. So the first disk is in the XY, X2 plane. The second disk is in the Y1, Y2 plane. And we can squish the x's and stretch the y's, and that does not affect the symplectic form. But one of the deeper phenomena of symplectic geometry or symplectic topology is when you take the symplectic product of two disks on 4. So now the first one is in the X1, Y1 directions. The second is in the X2, Y2 directions. This is no longer symplectomorphic to the small cross-bit disk, although they have the same topology and the same volume. And this is because of Gromov's non-squeezing theorem. Because the product of the two unit disks does contain the unit ball. And the unit ball cannot be squished into a symplectic disk of radius lesser than 1 in the X1, Y1 directions, even if you have no constraints in the other directions. A lot of activity on open subset of R2N has been on nice, there's a lot of activity of nice subset, convex set with smooth boundary, interiors of polytopes, including some very recent major results on those. But the sets I'm talking about today are very different from that. They're very non-convex. And this came out of a question raised a few years ago by Alan Weinstein and Christian Lohmann. What they ask is, you take a symplectic manifold, and you have non-compact symplectic manifold, and you have a ray shooting out to infinity inside the symplectic manifold. Rigorously, what this is the image of a proper embedding. The standard closed ray into the manifold. Being a proper embedding is equivalent to the image being an embedded whose image is closed. And what they ask is, well, can you excise? I'm forgetting what language they asked it, but is that excisable from them? And IE is the complement of that symplectomorphic to the ambient symplectic manifold. And when they asked it, it was just not clear which way this would go. Typically in situations like this, you would expect, well, in symplectic geometry, often obstructions come from hard techniques, for example, holomorphic curve techniques. Constructions come from soft techniques, covariant symplectic geometry, Moser method. So one expects, if the answer is no, maybe you need holomorphic techniques. If the answer is yes, maybe it's soft. But it wasn't even clear which way this would go. There's actually a very cute answer. So I mean, already in R2N, this was unclear. Very cute answer for R2N. I should at least mention it. When I told Leonid Potorovich about this, he thought for a minute and like, oh, here's why it works for R2N. If you take R2N, and you can think of R2N punctured at the origin as the symplectization of a sphere, of a contact sphere of dimension R2N minus 1. So R2N minus the ray would be the symplectization of this punctured sphere. And it is known that the contact structure, standard contact structure on the unit sphere, when you puncture it, it becomes contactomorphic to R2N minus 1. And when you symplectize, this becomes symplectomorphic to R2N. It's a beautiful, very elegant answer. We want something different. We asked the question about R2N because we care about general manifolds, and you can always find Weinstein neighborhoods that will identify the little neighborhood of the ray with the little standard neighborhood of the standard ray in R2N. So you really want to be able to have this excision be supported in a small neighborhood of the ray, the identity outside an arbitrarily small neighborhood of the ray. So maybe I'll write a couple of sentences here. Answer to the neighborhood theorem. And before we started collaborating, Shudi Tan has made kind of a breakthrough in this. He was able to find a symplectomorphism between the complement of the ray of in Rn and the ambient Rn. And he was able to make that be supported in a neighborhood that is parameterized by a small positive number. And these neighborhoods were getting smaller and smaller in the sense that their intersection is just the ray itself. But you see, the ray is not compact. In this situation, if you have an arbitrary small neighborhood of the ray, you cannot guarantee that it will be contained in one of these U-Balls alphas will be contained in this given neighborhood. And in fact, one can find tiny neighborhoods of finite volume, and in Shudi's case, the volumes of his neighborhood were always infinite. So this enables us to eventually excise a ray from symplectic manifold, but the ray in the manifold has to have a big neighborhood. And as Shudi and I were working together to improve this, and we were making progress, and then a paper came out for Stratman, who actually saw this, and our paper came later, and we saw this too, but our method is a little bit different, and we do more than Stratman does. So I will explain a little bit about what we do, and he does a very, very hands-on construction, and we have something that allows you to do things more generally and therefore excites more interesting set. So both his and ours are stronger than what I wrote on the board, but let me just write the basic thing. You can excise right from R to N, and you can make this excision be supported in arbitrary given neighborhood of the ring. And one of the consequences using Einstein neighborhood theorem is that you can in fact excise a ray for from any ambient symplectic manifold, and this itself also has a subtlety. In the first version of our paper, we sort of missed a detail, which I think was also missed in Shudi's earlier paper. It works, but it requires a little something. So
you want to say M is non-compact or something?
We want to have a closed submanifold that is diffeomorphic or homeomorphic to the ray. The ray is embedded properly, and that forces the manifold to be non-compact.
Oh, it's under the assumptions at the top. Okay, thank you.
Yeah, you are given an embedded ray. Yeah, you're right. Okay, let's say non-compact. This is in fact a necessary condition. Absolutely. Thank you, Chris. Okay. Now, there's actually a subtlety here, which is very typical of some of the stuff that happens here. Here's R2N. Here's M. Here's the ray. Here's the ray. Let's have some fun with colors. I'll try. Here's the Weinstein neighborhood. So basically, you want to be choosing a closed neighborhood of the ray in R2N, closed set containing open set containing the ray. You want to find a symplectomorphism of the complement of the ray with all of Rn. That is the identity outside the closed set. So here is the closed set. And then you want to sort of move it to here and then patch it with the identity map. And if you're not careful, you're going to get you might get something discontinuous because the closed set, it is closed inside the tubular the Weinstein neighborhood, but it might not be closed here. It is closed in R2N. Here, being closed in the tubular neighborhood does not guarantee that it's closed in N. So you have to be a little bit careful because you're starting with a proper embedding of array, and you extend it to a whole embedding of the Weinstein neighborhood, and that cannot be proper. The image is open. But because the embedding was proper on the array, you can actually find a closed set such that the restriction of the embedding to that closed set is proper, and then the image is closed as a map to the ambient manifold, and then the image is closed in the ambient manifold, and you're good. So you have to, and this is the type of stuff that again kind of becomes very slippery. You want your set to be very narrow as you go far away to guarantee that your things work. So. Proper just means that the image of a closed set is of a compact set is compact, and it guarantees that the map for nice spaces guarantees that the map is a closed map. So the image is closed. Okay, what next? So now you can, given that you can do this, you can start having fun. For example, you can iterate. So, for example, here's a symplectic manifold, and we call this a ray with two horns coming out of it. And what can you do? Well, think of the ray with two horns as the complement of one of the horns will be ray, and think of this as a complement of the ray inside a different manifold, which is the original manifold minus the ray and the other horn. So you keep excising. So that kind of gets to be fun. And let me give you the application that was the original motivation of Weinstein and Blowman. Whenever you have an exact symplectic form, it always has a non-vanishing primitive one form. So basically this was sketched, a proof was sketched by Weinstein and Blowman, assuming that you can excise array. The idea is very simple, very beautiful. You take an exact symplectic form, you choose a primitive one form, and you can actually perturb it while still keeping it a primitive one form on the same symplectic point. You can actually perturb it so that it becomes, so that it's zero, so it becomes discrete. And then each of the zeros, you're just sort of sending off to infinity using a long array. So they gave the sketch. This was later proved by other means without, I think it was before he excised the array, by the same guy, Bernd Stratman. Again, very hands-on. That's really hands-on in a way that really deals with all the subtleties. And then in our paper, Shudi and I took the sketch of Lohmann and Weitstein, and we actually added the details. Very cute application.
Okay.
Yeah.
So, in the iterate process, the two horns actually have finite volume, right? The neighbor of the horn has actually have finite volume.
Well, the neighborhood mostly remains. The neighborhood does, we have an excision supported in the neighborhood, but the only thing that gets removed is the horn itself, which has finite volume. And in fact, you're a little bit ahead of me. I think I was planning to say this in another couple of pages. In order to be able to excise a subset and have the excision be supported in arbitrarily small neighborhoods, that subset has to have volume 0. This is a necessary condition. Because you can always find a tiny neighborhood of finite volume. And if that's symplectomorphic to the complement of your set better have volume 0.
I see.
So that is a necessary condition, and this is true here.
Excuse me. About that application, that there exists like this non-vanishing primitive, is there some sort of like genericity about that? If I start from like some vanishing primitive, can I in some sense perturb it to become non-vanishing?
So, I don't know. So you can definitely perturb it so that the zeros become isolated. That you can do. And this was sketched by this you can do, and we give all the detail. I do not know a way of getting rid of isolated zeros except for this method. I just don't know. I don't expect you can do that, but I don't think. I don't. Good question. So what does Stratman do? So he pushes the ray away further and further, very hands-on iterative procedure. And really along the ray, you can just push it using a vector field that just sends the ray off to infinity. He uses a time-dependent vector field, and he sort of extends it using an iterative procedure. And eventually he's producing a time-dependent Hamiltonian vector field that does the job. And I will sort of quote from his paper. So he starts with the vector field along the ray itself, and he says there is little hope to extend this to Hamiltonian vector field on the manifold using local neighborhood models around isotropic manifolds. So we're very proud that we did achieve what he thought there would be little hope for. And in fact, our vector fields are Hamiltonian vector. So what do we do? What do we do? We are able to start with a vector field on this subset that you're excising, that just sends it off to, it's an incomplete vector field. Incomplete vector field sends it off to infinity in finite time. And then you extend it to an incomplete Hamiltonian vector field on your ambient manifold. Hamiltonian guarantees that the flow, wherever it is defined, will be symplectic. And you arrange it in such a way that the same piece sends off to infinity. And where's the pitfalls? The pitfalls is you want to be very careful to not send more things to infinity, and that's where it becomes hard. But once you do that, you can excise many more stats. I will say a little bit about that. So for example, if you have a subset of a manifold that is non-empty and whose complement is diffeomorphic or even homeomorphic to the manifold, necessarily that subset has to be closed. And the ambient manifold has to be non-compact. This is just from topological reasons. Now, if you have a non-empty subset of a symplectic manifold, with the property that not only you can excise it, but you can do this in arbitrarily small neighborhoods. So for every neighborhood U of Z, you can find a symplectomorphism that is supported in U, or let me just write identity outside U. Let's just write that. For this, as I mentioned verbally a minute ago, the volume has to be 0. So this is, in fact, this is going to be true for any manifold with a volume form. And let me show you an example just of types of sets that we are able to excise. One of them is, we like to call it a Cantor brush. So here's the manifold, and here is a Cantor set. And Cantor set, so Stratman already was able to excise a manifold cross array. Array, so the collection of arrays parameterized by a manifold. But we have, for us, the collection of arrays can be parameterized by any closed thing, for example, Cantor brush. And let me write this as a Cantor set in something of codimension 2 cross 0 infinity, and the directions actually matter. So this whole thing, for our method to work, we need this to lie in codimension 1, and we actually need the directions that shoot out to infinity to be the null directions in this codimension 1 thing in which our set lies. Let me do 2 more examples. Box. But we need some space there, so it has to have codimension 1, and the directions that shoot out need to be the null directions, and here's the tail of that box. Now, of course, you can do this by natural iteration. Remove the tail because you can excise array, and then remove a box. That is a special case of Stratman's result. But we can do it all at once. We can actually do this all at once using a kind independent, incomplete Hamiltonian fill. And both of these are special examples of epigraph. Epigraph is the region above a graph, except my graph is sideways. Here's R. And here is some 2n minus 2-dimensional manifold. And this is sideways graph of a function. But I want to take the stuff above the graph. And again, this should be embedded later in the symplectic manifold so that these up directions become null directions. So let me write the epigraph as Px. Oh, I'm sorry. I'm going to erase this. I need to make the correction here. So this is the set of Px where f is greater or equal to lambda p. There we go. I don't care so much about the left-hand side. I could have done R, but I actually want to allow infinity. So the graph doesn't have to lie in all of this. There can be a subset of sigma over which nothing happens, namely the subset where lambda is equal to infinity. There's nothing about that. And we need this epigraph to be closed, and condition for this to be closed is equivalent to this lambda being lower semi-continuous. And this being lower continuous, semi-continuous in contrast to being continuous is what allows you to get those kind of crazy examples supported on arbitrary closed set, etc. And the main tool here is the main important tool to address these guys is that a lower semi-continuous function can be approximated from below, can be written as a supermoon of a sequence of increasing smooth functions. Yeah.
Here and there, sigma is just an element to.
Well, any manifold, and then you just embed it in your symplectic manifold in such a way that the directions that shoot out are null directions inside the image of sigma cross R.
It has to be compact.
I'm sorry?
Has to be compact.
No, but the embedding has to be closed. Proper, I'm sorry.
Yeah.
Oh, embedding has to be proper. So the image has to be closed. Yeah, thank you. Now, actually, a very interesting question that we cannot answer. Up until now, all our examples that we can excise using this method are epigraphs. And we do not know if these are the only examples. So one can actually formulate this in a more formal way, but we don't know what the answer is. One of the subtleties is you take the guy that you excise and you sort of collapse it in these vertical directions. And the question is this going to be Hausdorff? One, if it is, then we can, anyway, but we don't know what the answer is. So I want to say a few words about what goes into the proof for excision using this technique. So this is, I would say, Hamiltonian excision. So, up until this project, I was very much afraid. Well, first of all, up until this project, I couldn't tell the difference between upper semi-continuous and lower semi-continuous. Never remembered which is which. And second, up until this project, if someone would say incomplete vector field, I was like, okay. But it turns out we're actually, we are actually using them and pushing them, and we can actually manipulate these incomplete vector fields, which is kind of cute. So let me say a few words about flows. So this is what we teach in graduate courses in manifold. You have a vector field in the manifold. And the vector field has a maximal flow. We specify the initial condition at the time, and then you just move for that time. So the flow domain, we call it dy. is a subset of M plus R that contains M plus 0. And one of the features of the, what we can call fundamental theorem of flows, is that this flow domain is open, and this is actually a non-trivial part of this theorem. So basically, what the game that you're playing here, you have the local theory of ODEs, local existence and uniqueness for solutions of ODEs. And you'd like to go from the local to the global. And, you know, if you open John Lee's textbook's Introduction to Fluid Manifold, well, you know, there's details there that, there's details. Yeah. So we can write the flow domain. We all know. As a set of all points, write this as. Let me put here, X will be the point of the manifold and T will be my time. Such that T lies in an interval, open interval. Possibly infinite. Containing 0. And here's my flow psi. So if you fix the point in the manifold, you're just solving the ODE. And then initial condition given by that point. And this is the maximal flow. So maximality means that you cannot extend this to a bigger flow line. All the flow lines are, even if the interval is closed, this maximality is going to be among open or closed intervals. Even if the interval is closed, you have another flow line with the same initial condition will be contained in the maximum line. And this implies that this, together with the uniqueness of local solutions of ODEs, implies that it actually, oh, I'm sorry. I wrote this incorrectly. Let me say this as implies, and I will say verbally. This is not the definition of maximality. Maximality means that you cannot extend it to a bigger flow line. And the corollary using uniqueness of local solutions of ODEs is that, in fact, it contains all other flow lines. Maximality means you cannot extend it. Corollary is it contains all of them. So there's a consequence of maximality. And openness will tell us that for the axis time, this is the function Ty. Is lower semi-continuous. and that the backward exit time is upper semi-continuous. And that the smoothness of the flow, smoothness jointly in both the manifold and time parameters, but in particular, when you fix the time parameters, you get the time to evolution, and then this now becomes a diffeomorphism between open subsets of your manifold. Then we know what we mean by excision. We just need the first manifold to be the complement of that, and the second manifold to be everything. This is the same as saying that the set that you excite coincides with the set of points where the forward exit time is less than or equal to 1, and everywhere the background exit time has to be strictly less than -1. But of course, when you have this situation, you can keep going back. So this implies that the backward exit time is in fact everywhere -infinity. And if you take the flow and you sweep the set Z, everything that flow into the Z itself, forward flow stays inside itself. If you sweep back, you're getting exactly the set of points where the forward exit time is finite. And one of the subtleties is that Z is closed, but if you take it sweep, if you take the set of all points that flow out in finite time, that might not be closed. So that's one of the subtleties. Symplectic excision, what are the steps of the proof? There's really two different pieces here. One of them is just excite smoothly, and I mumbled something about epigraphs being approximated from below by graphs of smooth functions. And you can use that to form smooth excision along null vector field, and this is something that is living inside a submanifold, and then the challenge is to take one say neighborhood and try to extend it to the rest of the manifold. And I think I want to focus on number 2. This is exactly what Brett Struckman expected would be difficult. It really is not trivial. So I guess the title here is going to be, well, from smooth excision to Hamiltonian excision. This now kind of the title for the last part of the talk. So I will give you the statement of the theorem and then some of the idea of the proof. So we start with a closed subset of a symplectic manifold. And we assume that you can actually extend it a little bit. It actually lives inside a submanifold. Here's a inclusion map. And that we're given an excision along this submanifold. Given by a vector field y. And this is assumed to satisfy two assumptions. First of all, this is a null vector field. And second, what I just said verbally, the time one flow of y excises that from N, i.e. is a diffeomorphism from the complement of that in the submanifold to the submanifold. We've run out of space. So these are the assumptions, and I will write the conclusion of the theorem all the way on the left-hand board. I had another version of the paper in the archive, and the theorem used to be a lot more complicated. So I'm very satisfied with this version. Let me give you the conclusion. Actually, the conclusion is short. I can do this here. Sorry, I've been dreaming. Okay, let me put the conclusion here. Then there exists a smooth map without function of the manifold. Whose time one Hamiltonian flow excises that from bigger ambient manifold. That's fit here. And then just as a tiny reminder, this is, yeah. Basically, this will be the time on the flow of the vector field that satisfies the usual Hamiltonian equation. So let me give you the idea for the proof. It's going a few steps to have. Okay, I think I'm okay. Let me give you the idea of the proof. First of all, let's take the contraction of the vector field against omega. So if you're pulling back to the submanifold, that's zero by assumption. But at points of the submanifold, you can evaluate this also with vectors that are not necessarily tangent to the submanifold. This is a real valued function, a fiber-wise linear real valued function from the tangent bundle of the ambient manifold evaluated on your submanifold. Vanishes on the tangents to the submanifold. This is just the normal bundle, just fiber-wise linear function of the normal bundle. And at this point, the Weinstein tubular neighborhood theorem kicks in. And you can identify a neighborhood of the submanifold with the neighborhood of the zero section in the normal bundle. And what you get, Weinstein is the theorem. You got function h from an open neighborhood of the submanifold. That has the property that its Hamiltonian vector field simply restricts to the given vector field on that submanifold. So this is good news. So you can just take the Hamiltonian flow of this function, but now there's a couple of problems. One of them that is this is defined only in a neighborhood, so that's not too bad. You can use a bump function to extend it everywhere, but the big problem is that you might be exciting too much. And again, one of the subtleties is you can take so this is a technical thing, the closure inside this neighborhood where the function h is well defined. You take the closure of the sweep set inside the set where this is well defined, but might not be closed in the ambient manifold. So now comes a technical lemma. That's kind of where the heart of the challenge is. There's a very cute argument that once we achieve the technical lemma, how to finish. We'll see how much like that too. What is the technical lemma is that you can actually find a closed neighborhood C of Z in M that has the following properties. First of all, C is contained in this open set, open sort of in this Weinstein neighborhood. Second, maybe I'll enumerate these. Here's number one, and here's number two. The restriction of H, well, the function H, the way we constructed it, it vanishes on N, in particular, it vanishes on the set Z that we're trying to excite. It turns out that in this situation, if you choose a careful enough of choosing a closed neighborhood, the function will vanish at infinity. You can choose a closed neighborhood such that the vanished restriction of the function at up to that closed neighborhood vanishes at infinity. What does that mean? It means that for every positive number epsilon, the set where the absolute value of the function is greater than or equal to epsilon inside our closed set is compact. That's requires a cautious choice of this closed neighborhood. And number three is the most challenging one. You would like to choose the neighborhood again to be very narrow as you go far away, in such a way that you see, if you take a maximal forward or backward trajectory of your flow, in this case xh, maybe it's defined for all positive times, or maybe it escapes to infinity. This is by the escape lemma. So if it is only not defined for all positive times, it has to escape every compact subset. In this case, subset of the tube of the Weinstein neighborhood. But in that situation, we want to choose C to be narrow enough so that you will exit C. So let me write this formally. For every maximal forward or backward. Respectively, trajectory of this Hamiltonian vector field on the Weinstein neighborhood, if it is contained in this closed neighborhood whose properties we're describing, but not in the closure in the Weinstein neighborhood of the set of points that get excised, then it is defined respectively for all positive or negative terms. Now, okay. And this closed neighborhood that gets very narrow as equal to infinity is sort of the key to extending our Hamiltonian flow in a way that does not excise more than we want to excise. So at this point, take any cone function, values, smooth function values in 0, 1, the following properties. And it has to be 1 on the set that we're excising, because there we don't want to touch anything, want to keep excising it. And the slab support, namely the closure in M, the set of points where it's non-zero, is contained in this neighborhood, closed neighborhood C. And here's a cheap one. At each point, if chi vanishes, then so does d chi. This is, you just take your chi, you square it, very good. And then you multiply your Hamiltonian function that was defined on the Weinstein neighborhood by this cutoff function, extend by 0. So this now becomes smooth. And claim the time 1 Hamiltonian, let's say, time on flow of the Hamiltonian vector field of F excises that from to give a piece. I think I have like 2 minutes left. Okay. And the idea is on the manifold you have different region, and each region you get your excision for different reasons. And again, the challenge is to not excise too much. So for example, on the set where F is non-zero, well, this Hamiltonian full flow of F, so it preserves level set. So you take any non-zero level set, for example, the level set is contained. This you're sort of the function h stays away from 0 for example, absolute can be the. This is because f was h times something between 0 and 1. And this is inside. Of course, it's also contained in the support of C of chi. So the level sets are contained in a compact set. So these level sets are good. The flow stays in a compact set, so you're good. So defined for all positive and negative times. On the set where chi is equal to 0, because we arrange that not only chi but also the differential of chi vanishes on this set, the vector field is just 0. So again, so the flow is defined for all times. And then the entrancing set. Now, each of these first two sets is invariant under the flow of Hamiltonian flow of F, so therefore the complement is also invariant under the Hamiltonian flow of F. And the interesting set is the complement, which is the set where F vanishes, but chi does not vanish. So here again, you have to sort of break it into different cases. First of all, on this, let me just say it very briefly. On this set, first of all, because F is 0 and chi is not 0, H has to be 0. And therefore, on this set, let me see, where is it? Yeah, the differential of F will be equal to chi times the differential of H. So this is, and therefore the flow of F is given by chi times the flow of H. And because this set is invariant, your trajectories for F will remain everywhere on this set. And as a consequence of the outside the set, these two vector fields might become different, but as a consequence of the escape lemma, if you have a forward or backward trajectory of F that stays in the set, which is maximal for F, it will also be maximal for this other vector field. So you're never going to exit this set, even if you're flowing for this other vector field. So you're staying in this set. So then all that you're doing is just a flow for the original vector field, but you're going a little bit slower here. You have to be cautious with what's happened. Now, if you did just flow for XH, then you might exit this set. Okay, the flow for XH might exit this set. Then I think my time is done. So let me just say, you divide this into several cases here with this. Now this set is also contained in C. So the two cases are flow lines that start in C versus C minus that famous set Q versus C in Q. And because you're going slower than the original vector field, as long as you're staying in the set, the original vector field, the trajectory is defined for all times, so is the new one. Because of the choice of C, such that flows for XH that have that exit in finite time has to leave C, but then you're going to reaching the region where chi is 0. So those finite flows of H that might expect, which is the one that might escape, that give us all the trouble, because of the careful property 3 of C, the corresponding trajectory of F, which starts at the same point, actually will be defined for all positive or negative times. And, basically there's some details. I think I'm out of time. Thank you very much. Shudi Tang and myself. So this is in our paper. And that's
So here your exciting vector field inside M actually will possibly move C around, like it might not just like
Z has to stay. So because this is a time independent vector field, okay. So Z is Canadian. Z is a set of points where the forward exit time is lesser than or equal to 1. If you move forward, the forward exit time gets even smaller. So you're staying within Z. It's a time independent. And that's actually very, very, very important part of this argument. So that Z actually gets sort of swept to infinity. So for example, I showed these iterations of when you remove one variable after another, that you cannot do all at once. The iterations, when you have these ray with two horns, you cannot do this all at once with one vector field. No way, because you're never gonna cross the thing.
So here Q is actually Z or,
No, Q is the sweep of Z. So Z is the set of points that exit at time lesser than or equal to 1. Q is the set of points. You first of all take the set of points that exit within finite time. These are exactly the things that flow into that. And then you take the closure inside the Weinstein neighborhood. So there's some details at the very end, but yeah. So kind of the points of topology turns out to be the most kind of subtle stuff. Yeah.
It seems to involve in a line sense that, like you could choose Z to be a higher dimensional string, for example, any isotopic setting.
Yeah, no, absolutely. Anything that's sitting, yes, that can be a high dimension. You do need co-dimension, at least one. We need space to do that Weinstein neighborhood. And then you need that have to have co-dimension at least one, but you can have co-dimension one for sure. As long as, but then you have to be very cautious with the direction in which you go on. Yeah. So the easiest is if you start with something contained isotropic or contained in Lagrangian, then there is the challenge of the smooth excision already there. There's a question we do not know how to answer, whether the stuff that you can excite has to be an epigraph, that we don't know. But then the challenge is only if you're starting with something isotropic or sitting inside Lagrangian, the only challenge is the smooth excision. And then there's no problem then you don't have to worry about directions because all directions are null directions in that case.
Other questions? So could you explain your motivation for remove the ray with the two horns?
It was just a curiosity. So when I saw this, that was the first question I asked, like, oh, can you do this? And I asked some people and no one knew. And then it turns out, so it was like, how far can you go? So, what kind of shapes can you remove? But then again, the ray with, so Shudi Tang, my co-author, he had a whole hierarchy of different types of excision, and he can actually show they're all different from each other. So this is the one that has the most flexibility, but it's also the most restricted one. So here we're sizing by time on maps of incomplete Hamiltonian flows of a function that vanishes on the set that is being excised. And that gives you even something I did not say explicitly, just the fact that if you can do this, then you can do this on arbitrary small neighborhoods is actually non-trivial. The ingredients that go into that are kind of not far from some of the ingredients that go into here. But then there's other ways of excision, which don't have the flexibility, but that do allow you to excise more things in special cases. And then Shudi Tang has a whole hierarchy of things. So the ray with the two horns or more complicated closed graphs with roots at infinity, these can be excised by iterations, but not by Hamiltonian excision. They never pass through these functions.
Other questions? All right, let's thank Peter again. We'll have a 15-minute break before I